Good night, everyone, and welcome back to Fundamentals of Engineering with Farhad, Mechanics of Materials, Maximum Stress Calculation. In this example, we have a flat bar, long steel flat bar, which is handling a eccentric axial load of 32 kilonewtons, and there is two holes between our bar. So there is a small hole with diameter of 20 millimeters at A, and there is a larger hole, circular hole at B with a diameter of 50 millimeters. When we apply a force of 32 kilonewton at its free end, we want to know what is the maximum stress at A and B. If you remember, we talk about the stress concentration near a circular hole in a plate. Like you can see, the radius and diameter of the plate is given, and when we apply a pulling force, you can see the stress concentration in the vicinity of the hole is much higher than the farther area. Mhm. So if you develop the stress distribution near circular hole, you can see this is sigma maximum, this is sigma maximum at the far end, and we use like sigma average for our study. Mhm. Likewise, we need to jump to a chart for flat bar with holes and read the ratio of uh, diameter of the hole to the width of our plate, which is provided here. D here is equal to 100 millimeters, and R 2R is the diameter of hole A and also hole at B. We want to calculate the maximum stress in both of these circular holes. So at A, for example, at first we concentrate our attention on a smaller hole. Radius is half of diameter, and that's 10 millimeters. D, small d, is equal to capital D minus 2R, and that's 100, which is the depth of the plate, minus a diameter of the smaller hole, which is 20 millimeters, 2 times 10, that's 80 millimeters, and net area in tension is equal to D times T. The thickness of the plate also is provided to be 15 millimeters, and D is equal to 100 minus 20, which is 80, and that make it like 80 times 15 millimeters, it's equal to 1200 millimeters. Convert that to meter, that's 1.2 times 10 to negative 3 meters squared. Mhm. My bad, it's like 12 millimeters. It should be here. Mhm. And then if we just jump to our chart to read the K factor, so 2R over D is equal to diameter of the smaller hole to the width of or depth of the plate, that's zero point 0.2. And if you read that based off our graph, you need to climb up and read K value, that's K for the circular hole, and it just gives us a K equal to 2.5. And in calculation of sigma maximum, and be careful, this sigma maximum is K, a coefficient for a factor for that circular hole times pulling force over the area net. So we have our K value 2.5 from the chart times 32 times 10, that's 32 kilonewtons, over the area which we net area which we already calculated to be 1.2 10 to negative 3 meters squared, and that gives us sigma at a 66.67 megapascal. Likewise, at B, we have to calculate. This time we are here. We talk about the larger hole now. Mhm. And radius is equal to half of 50 and 25 millimeters. D is equal to depth of plate minus 2r, which is 50, and that gives us a D. Small d is equal to 50 millimeters. Area net is small d times thickness of the plate. Thickness remains the same, and it's this time 750 millimeters squared, and convert it to meters to give you this numeric value. Again, 2 small r over d is equal to 50 over 100, and that's zero point 0.5 this time. And if you read it from the chart, this time climb up from our chart and read the K value this time. Sigma maximum is nothing but K times pulling force over the net area. You can read K value between 2 and 220, and it's almost 217, 218. We use 217 for that, and use that in the formula. It just gives you 2.17 times pulling force over the net area, which we calculate in previous part. That's 92.6 megapascal. And there is a question: if we have such a configuration in which in the vicinity of which hole maximum stress is higher. So let's think about it for a few seconds. A or B? If we come to a conclusion to answer our question, in the vicinity of which hole maximum stress is higher, sigma maximum for A is equal to 66.67. This is this part, sigma A, and sigma maximum at B is equal to 92.6, and definitely sigma maximum at B is higher in comparison to A. And the reason for that is the net area is decreasing. That's why sigma maximum increases. Thank you. We'll solve more problem related to stress calculation in next videos.